Dear interstellar traveler, please close your eyes. Let your breath gently synchronize with the heartbeat of Earth. This is a scientific harbor for souls yearning for peaceful sleep. Tonight, let us spread a gentle blanket of knowledge across the vast sea of stars. The sleepy fact you are about to hear are like specks of thought dust drifting in the cosmic depths. Did you know Jupiter continuously plays an infrasound symphony with frequencies 1,000,000 times lower than the human hearing threshold? The pulsar in the Crab Nebula flashes every 33 milliseconds, a cosmic timekeeper more precise than an emerald pocket watch. These relaxing astronomy facts will weave into the most unique, calming space documentary, projecting a personalized space documentary for sleep deep within your consciousness. Imagine a distant future, far beyond human memory, where even time itself seems stretched thin. When the sun no longer meets our needs, the air begins to tremble inexplicably, as if the very earth fears the horizon. A faint glimmer in the sky suddenly transforms into a blazing wall of heat spanning heaven and earth. The azure dawn loses its gentleness, becoming a churning sea of fire. The fiery waves seem to breach the sky, engulfing the entire world. Hey everyone! Mountains and oceans vanish without a trace in an instant of scorching heat. Corners once ruled by darkness now retain not even a shadow. Light and heat fill every inch of space, erasing all traces of the past over millions of years. The sun's core will continuously expand. Each sunrise is no longer a signal of hope, but pushes us one step closer to agony. One day, eventually, there will be no more glowing horizon. All things will burn in endless flames, leaving not even ashes behind. Soon, this burning planet will continue to expand, passing beyond Venus's orbit, even engulfing Earth itself. Rocks will melt into magma under intense heat. Oceans will boil away into steam. The last breath of life will utterly dissipate under that impenetrable curtain of flame. Gravity will act like an invisible hand, pulling our scarred planet inward, dragging it into the gaping maw of this aging star. This is the inevitable fate of our star, and all the planets orbiting it in this final act. The sun will take its children with it. The question is never if it will happen, but when it will happen. The story of our solar system might end here, for 0.5 billion years ago. In a quiet region of the Milky Way, a vast molecular cloud lay dormant, like a mist holding the universe's past. Its gases were composed of hydrogen, helium, and dust, materials originating from previous generations of stars. The remnants scattered by a dying supernovae, seeding this nebula with life-forging heavy elements like carbon, oxygen, and iron, sowing the seeds for the future solar system. When a supernova's shockwave struck this molecular cloud, the gas was compressed to a point where gravity could take hold. Dense clumps began to form, continually collapsing. As they contracted, their rotation sped up. At the center of one such clump, pressure and temperature kept rising until a protostar was quietly born. This celestial object was still shrouded in thick dust, emitting only faint light in the infrared spectrum, like a cosmic infant swaddled in its cradle. Material from the surrounding accretion disk spiraled into this young star. Hot plasma jets erupted from its poles, carving out cavities in the nebula like an infant's tiny hands. pushing aside the surrounding mist. Millions of years later, the protostar's core temperature reached 10 million degrees. Hydrogen nuclei began fusing into helium. At that moment, the star ignited its thermonuclear engine, officially beginning its life. Once nuclear fusion stabilized, the Sun entered its main sequence stage, a long, stable period that would last for billions of years. Its light scattered the remaining surrounding gas, leaving behind a disk suitable for planet formation. This was the beginning of our star's life, forged from cosmic remnants, ignited by gravity, shining steadily at the center of the newborn solar system, like a lighthouse guarding its home. But to understand why this star will one day expand and consume the inner planets, we must first pierce its fiery surface. To see the hidden structure within the Sun's center is the core, an intensely dense thermonuclear furnace with a temperature of approximately 27 million degrees Fahrenheit. Under immense pressure, hydrogen atoms fuse into helium here. Every second, hundreds of millions of tons of hydrogen transform into new elements, releasing the energy that makes the sun shine. This process holds the ultimate secret of why the sun and illuminate the solar system. We will explore it more deeply soon. The solar core extends to about 1/4 of its radius, roughly 100 miles from the center. Beyond this range, its energy begins to diminish. Outside the core lies the radiative zone, a vast inner shell. Energy generated in the core radiates outward here in the form of photons, but these photons never shoot straight to the surface. The radiative zone is extremely dense. Each photon's journey is like an endless maze. They travel a zigzag path, constantly bouncing between particles, experiencing countless absorptions and remissions. Although photons move at light speed, they are always hindered by invisible forces. A single photon takes a full 170,000 years to barely penetrate to the next layer in this deep region where even light must slow its pace. The flow of energy is as slow as the settling of time itself. As we continue exploring outward, we encounter a significant transition. At about 70% of the solar radius from the center, the temperature drops by millions of degrees, and the density decreases sharply right here. The method of energy transport changes completely. We enter the convective zone. This is a turbulent outer layer, about 125,000 miles thick. Here, the solar plasma is cooler, approximately 6.5 million degrees Fahrenheit at the bottom, dropping to about 10,000 degrees Fahrenheit at the surface. This temperature is just right for heavier ions to retain some electrons, making the plasma more opaque to radiation. Trapped heat causes the plasma to boil like water. Hot gas from below, being less dense, rises, forming massive columns of flowing gas. Upon reaching the top of the convective zone, the gas cools and sinks back down. This is a vast, churning ocean of plasma. Each rising column is the size of a continent. When energy reaches this layer, its escape is much faster. Convective currents need only a few weeks to transport heat to the surface. If we could hover just below the sun's visible surface, we would see a pattern of undulating granules, like a pot of gently simmering soup. Countless hot plasma bubbles surge upward, while cooler plasma sinks down. In fact, close-up images of the sun from Earth also show these cells. They are called granulation. Each granule is about 600 miles in diameter. The bright center is where hot plasma rises, and the darker edges are where cooler material sinks. Each granule lasts only a few minutes before being replaced by new cells. A never-ending dance performed by plasma. Closer to the surface, there is a thin yet crucial boundary, separating the radiative interior from the convective exterior. This is the tachocline. It is a shear layer, where the star's internal rotation rate changes abruptly. Deep in the radiative zone, the sun rotates almost like a solid ball, with a rotation period of about 27 days. But the overlying convective zone rotates quite differently. The equatorial region spins faster, with a period of about 24 days, slowing towards the poles, where the period can be up to 34 days. The tachocline lies at about 0.7 solar radii from the center. This difference in rotation speed creates intense shear here. Scientists believe the sun's magnetic field is born right here. Electric currents in the conductive plasma act like invisible hands, continually amplifying magnetic loops. Essentially, the tachocline acts as the sun's magnetic dynamo. The turning and stretching of magnetic field lines in this layer form the global magnetic field permeating the entire star, and also govern the solar activity cycle. It is from this thin, invisible interface that everything from sunspots to solar flares is born. They are the hidden power the sun reveals to the universe. Following the convective currents upward, we finally reach the photosphere, the sun's visible surface. The luminous sphere we see with our naked eyes. Technically, the photosphere is not a solid surface, but a layer of thin gas about 250 miles thick. Here, the plasma density is low enough that photons can finally break free and escape into space. The light that started from the core after a journey of hundreds of thousands of years is emitted from this layer, traveling through the solar system at light speed, illuminating every planet. The average temperature of the photosphere is about 0 degrees Fahrenheit, though far lower than the core's infernal heat. It's still enough to make metals glow white hot. The sunspots, filaments, and granulation we observe through telescopes are all located in this layer. Sunspots, those dark patches visible on the photosphere, are the most obvious marks of the sun's magnetic restlessness, like strange discolorations on a giant beast's skin. They are formed by strong magnetic fields with temperatures much lower than the surrounding areas. The magnetic field within a sunspot suppresses the convective motion of hot gas beneath it, cooling and darkening these regions, creating a stark contrast with the bright surroundings. Sunspots usually appear in pairs or groups with opposite magnetic polarities, a sign of magnetic flux tubes extending outward from the sun's interior like hidden magnetic needles. Within the sun, they can last from days to weeks, some even larger than Earth. Around active sunspots, we often see bright faculae and plages. These are regions of highly concentrated magnetic fields, making these parts of the sun slightly brighter than their surroundings, like faint glows blooming around the dark spots. Meanwhile, the entire photosphere is covered with ever-changing convective granules. Each granule is a Texas-sized bubble of hot plasma, constantly forming and dissipating, never ceasing above the photosphere. The Sun's atmosphere extends into two other main layers, the chromosphere and the corona. The chromosphere is a fragile region directly above the photosphere, only a few thousand miles thick. Because the photosphere is so brilliant, the chromosphere is usually nearly invisible, but during a total solar eclipse, it appears as a thin, jewel-red edge, like a red necklace adorning the sun. Surprisingly, the chromosphere's temperature increases with height, from about 7,000 degrees Fahrenheit at the bottom to 14,000 degrees Fahrenheit or even higher at the top. This inverted temperature gradient remains one of the sun's most puzzling mysteries. As if moving away from the fire makes it hotter, the chromosphere's structure is shaped by magnetic fields covered with dynamic jets called spicules. Like upward shooting blades of plasma, these spicules are narrow, geyser-like eruptions, lasting only minutes at any moment. Across the entire chromospheric network, up to 10 million spicules are erupting, reaching heights of 3,000 to 60 miles at speeds of 30 to 60 miles per second. They hurl hot plasma into the outer corona, perhaps playing a crucial role in the heating of the corona. Viewed through special filters, the chromosphere shows a network of bright regions, highlighting larger-scale convective cells, known as supergranulation. Above the chromosphere lies a narrow transition region only a few hundred miles thick, where the temperature skyrockets from tens of thousands of degrees Fahrenheit to nearly 1,000,000 degrees Fahrenheit, as if passing through an invisible heat barrier. Beyond the transition region lies the sun's outermost layer, the corona. Corona comes from the Latin for crown. It is a vast plasma cloud extending millions of miles into space. During a total solar eclipse, the corona appears as a pearly white crown, encircling the sun. The visible streamers and loop-like structures are shaped by the sun's magnetic field lines, like silver threads hanging from a crown. In the corona, ions possess extremely high energy, radiating mainly in X-ray and extreme ultraviolet wavelengths. They are the most mysterious language of the sun's outer atmosphere. But why is the sun's outer atmosphere so incredibly hot? Far hotter than the underlying photosphere, this remains one of the biggest unsolved mysteries in solar physics. It's like moving away from a fire, yet the air gets hotter. Behind this counterintuitive reality lies a mechanism we still don't fully understand, a puzzle the sun seems to have deliberately left for humanity. The corona has no upper boundary. It gradually blends into the solar wind, a continuous outward flow of charged particles, the breath exhaled by the sun, enveloping all planets and bodies in the solar system. This dynamic structure makes the sun more than just a cool light bulb in the sky, but a living, breathing star, a cosmic giant hiding countless secrets. However, to truly understand why the sun shines, we must dive back into its central inferno to study the engine at its core, the universe's most secret alchemy driving it all. In the solar core, under extreme density and scorching temperature, a near miraculous process is quietly unfolding, hydrogen fusing into helium. Here, Einstein's famous equation manifests itself. Mass is converted into energy, becoming the source of the sun's light. The dominant fusion cycle in the sun is called the proton-proton chain. This series of nuclear reactions might sound like obscure terminology, but in reality, it is the story of sunlight's birth, the cosmic drama playing out day after day in the sun's core. Imagine the protons, bare hydrogen nuclei, zipping around in the core's chaos. Normally, they would act like the magnets with the same pole, strongly repelling each other due to their positive charges, never able to get close. In fact, according to classical physics calculations, protons in the sun's core could never overcome this electrostatic repulsion, let alone fuse. At the core's temperature, the probability of the protons getting close enough to fuse is almost zero, but the sun still shines. It still releases energy into the universe. The key to the seeming paradox lies hidden in the enigmatic world of quantum mechanics. A proton is not just a particle, it is also a wave. Its position becomes blurred in the quantum haze. This makes a phenomenon called quantum tunneling possible. Particles can tunnel through energy barriers that are insurmountable in classical physics. Like finding a hidden back door in space-time, this means that in the solar core, despite the incredibly low odds, protons can get close enough for their quantum wave functions to overlap, tunneling through that repulsive barrier. As if by a quantum stroke of luck, they find a concealed path, ultimately merging, and when they merge, something extraordinary happens. They fuse into a heavier atomic nucleus. This wonderful encounter is the first step of the proton-proton chain. During the fusion of the protons, one proton, under the influence of the weak nuclear force, transforms into a neutron, ultimately forming a deuterium nucleus. This reaction releases a burst of energy in the form of a positron, and an almost massless particle, a neutrino. The positron almost immediately annihilates with a nearby electron, releasing gamma radiation. The neutrino, this so-called ghost particle, hardly interacts with any matter. It escapes the solar core at near light speed, carrying away a tiny amount of energy, like a silent messenger. Interestingly, billions upon billions of these neutrinos pass unobstructed through every inch of Earth every second, through your body, leaving not a trace. They are secret letters from the solar core to the universe, tests that very few can read them. Next, the newly formed deuterium nucleus doesn't last long. In the second step, it collides with another proton, forming helium-3. This reaction releases a burst of high-energy gamma photons, like a flash signal of this nuclear reaction. Finally, in the third step, the helium-3 nuclei collide and fuse to form helium-4, releasing to excess protons in the process. These protons, no longer part of the final product, return to the core's chaos, perhaps to participate in fusion again. This step also releases energy, adding more fuel to the sun's light. In summary, the net result of the proton-proton chain is 4 protons ultimately fuse into one helium-4 nucleus, and in this process, some mass is lost, converted into energy. The mass of a helium-4 nucleus is slightly less than the total mass of the 4 protons that formed it. This lost mass is converted into energy in the form of gamma rays released, becoming the primary energy source in the solar core. It is this mass-to-energy conversion that provides the sun with its continuous power. filling its core with high-energy photons, allowing it to shine for billions of years. Theoretically, this chain reaction might seem complex, but it occurs on an unimaginably vast scale in the solar core. About 4 BY protons fuse into helium every second. In simpler terms, this is equivalent to hundreds of millions of tons of hydrogen fusing every second. The energy released by these reactions is staggering. The Sun produces about 4 BY watts of energy per second, equivalent to billions of 1 megaton nuclear bombs exploding simultaneously, yet the Sun's light always reaches Earth in a gentle manner, as if deliberately tempering its ferocity. But even so, for an individual proton, nuclear fusion remains extremely rare. Most protons bounce around in the core billions of times per second without ever fusing, but the number of protons in the solar core is so immense that even if only a tiny fraction undergoes fusion, it's enough to sustain this enormous energy output, keeping the Sun shining steadily in the universe. The high-energy gamma photons produced by these fusion reactions begin a long journey outward. At the moment of their birth, they carry the most primitive form of sunlight's energy, the hottest embers of the solar core. But as described before, these photons must pass through the radiative zone, and this journey is fraught with obstacles. Gamma rays can travel only a fraction of a millimeter before being absorbed by ions in the core's dense plasma. The ion then re-emits a photon in a random direction. With each interaction, the photon's energy decreases slightly. After countless absorptions and re-emissions, the original high-energy gamma rays gradually transform into a crowd of lower-energy photons. First X-rays, then ultraviolet, finally becoming the visible light our eyes can see. The light that ultimately escapes from the photosphere is mainly visible and infrared light, the sunlight we feel every day, softened only after hundreds of thousands of years of refinement. It takes hundreds of thousands of years for energy to travel from the core to the surface. Light that once released from the photosphere, it takes just 8 minutes and 20 seconds to cross the 93 million miles and reach Earth. The noon sunlight that warms your face might have been born in the solar core when early humans were just learning to use fire. It carries hundreds of millennia of cosmic memory, gently landing on your skin. But the sun is no quiet beacon. Beneath its steady glow lies hidden restlessness, like a slumbering giant occasionally stirring. From its surface to its outer atmosphere, the sun constantly exhibits various magnetic phenomena, sometimes erupting with world-shattering power. Long before Galileo invented the telescope, ancient Chinese astronomers had already observed sunspots. Those dark spots moving across the sun's surface, the earliest evidence humans found of the sun's unrest. In these regions, magnetic field lines penetrate the photosphere, inhibiting normal thermal convection. The magnetic field strength here is extremely high, reaching thousands of Gauss, compared to Earth's magnetic field of about 0.5 Gauss. A contrast like a stream to an ocean. As mentioned, sunspots usually appear in groups and are often mirror image pairs with opposite polarity. Magnetically, giant magnetic loops connect these polarities, arching above the solar surface like invisible bridges, trapping and guiding hot plasma. These structures are like temporary scars on the sun's face, marking areas of concentrated magnetic tension. And where there is tension, eruption is possible. The most violent solar eruptions, solar flares, typically occur in complex magnetic regions around sunspots. Like the roar of an angered giant, a solar flare is essentially a stellar-scale explosion. When magnetic fields twist, move, and suddenly reconnect, vast energy is released in seconds in sunspot groups. Opposite magnetic poles are sometimes pushed together. If the field lines suddenly rearrange, the stored energy is released instantly, like a tightly stretched rubber band snapping. A solar flare can heat material to tens of millions of degrees in minutes. X-rays and extreme ultraviolet radiation burst outward, along with vast numbers of charged particles. The energy of a large flare is almost unimaginable. The most powerful flares release energy equivalent to 1 billion 1 megaton nuclear bombs, exploding simultaneously. We often observe to bright ribbons in the chromosphere on either side of a magnetic neutral line connected by glowing plasma loops, a temporary mark left on the solar surface during the energy release, closely related to flares, yet distinct, are coronal mass ejections, CMS. A CME is a huge cloud of solar plasma and magnetic field ejected from the corona into space, often accompanying flares or filament eruptions, like the sun spitting out a ball of fiery heat. Imagine a giant magnetized plasma loop or filament in the corona becoming unstable. It breaks free from the sun's magnetic confinement, hurling billions of tons of material into the solar system. As a CME unfolds and expands, its scale can surpass the sun itself, though the internal plasma remains extremely tenuous. It's like a vast yet lightweight cloud of fire. CMS race outward at speeds of millions of miles per hour. Some recorded speeds reach 1,000 to 100 to 2,000 miles per second, far faster than the average solar wind. When directed towards Earth, it becomes a space weather event 1 to 3 days later. This plasma cloud and its embedded magnetic field reach Earth, engaging in an invisible collision with our planet. Through flares and CMS, our star can directly affect Earth and impact human technological systems. Each of its mood swings can trigger chain reactions on Earth when the sun's high-speed charged particles and magnetic shockwaves collide with Earth's magnetic field. They can trigger a geomagnetic storm. The most harmless yet beautiful result of such a storm is the aurora. The aurora borealis in the northern hemisphere and aurora australis in the southern hemisphere. They occur when energetic particles spiral along Earth's magnetic field lines and finally collide with the upper atmosphere. These particles excite atmospheric gases, making the air glow like gas in a neon tube. Green curtains of light appear in the polar skies, sometimes accompanied by red, blue, and purple hues, like a flowing canvas unfurled in the sky. It's the most beautiful gift the sun leaves Earth, in its tantrums and direct proof of its power. But solar flares can also have more dangerous consequences. Intense geomagnetic storms can disturb the ionosphere and upper atmosphere, disrupting radio communications and GPS signals. throwing human technology into chaos. They can also induce harmful electric currents in long conductors like power lines and pipelines, so-called geomagnetically induced currents (GIC). For example, a strong solar storm in March 1989 triggered massive GICs, causing a complete collapse of the power grid in Quebec, Canada. Millions suffered a 12-hour blackout. The aurora from that storm was visible as far south as Florida. The sun's influence reaches far deeper than we imagine. Looking further back, in 1859, the solar storm known as the Carrington event was the most violent on record. Telegraph wires spontaneously sparked, even igniting paper in telegraph offices, as if the sun had suddenly reached a scorching finger towards Earth. Scientists warn that a Carrington-level event today would have even more severe consequences. Widespread blackouts could last for weeks or even months. Satellites would be damaged, navigation systems would fail, radio communications would be disrupted. Human civilization, reliant on modern technology, is far more vulnerable than in the 19th century, and more susceptible to the sun's influence. In 2012, we had a narrow escape. A Carrington-level CME erupted from the sun, but fortunately, Earth was not in its path. It swept through Earth's orbit, missing us by just a few days. Had it not, the storm in July 2012 might have become one of the worst natural disasters in human history, remembered forever. Solar flares and CMS directed at Earth collectively affect satellites, astronauts, airlines, and power infrastructure. Intense radiation and charged particle bombardment can cause satellite short circuits or even permanent damage. The magnetic field of a strong CME can also compress Earth's magnetic field, generating currents strong enough to burn out grid transformers. Once damaged, repairing such equipment can take months or even years. Even at moderate levels, solar activity, by heating the upper atmosphere, increases atmospheric drag on satellites in low Earth orbit. A mere twitch from the sun is enough to turn human technological achievements to dust. Notably, astronauts working on the International Space Station or future crews on lunar or Martian missions, stripped of Earth's atmospheric protection, also face risks from radiation spikes during such events. Solar radiation is an obstacle that must be overcome in humanity's exploration of deep space. Thus, monitoring space weather isn't purely academic. It's crucial for protecting human infrastructure and ensuring safety. We must constantly watch this star's moods to prepare before its temper flares. To the casual observer, solar activity might seem random and sporadic, devoid of pattern. But through decades, even centuries of study, astronomers have discovered a remarkable regularity. Solar activity cycles between active and quiet periods, like astronomical seasons. This is most evident in the rise and fall of sunspot numbers. The number of sunspots increases and decreases in a cycle of approximately 11 years. At the cycle's peak, for weeks, hundreds of sunspots might dot the solar surface. Like a sudden increase in spots on a giant's skin, at the cycle's minimum, the sun's face might be devoid of any spots for days, or even weeks, appearing exceptionally calm, as if the giant has fallen into a deep sleep. This pattern was first discovered by Samuel Heinrich Schwab in the 1840s and has remained consistent since detailed records began. Today we call it the 11-year solar cycle, or Schwab cycle, during solar maximum. The star's magnetic activity is most intense, and space weather effects are stronger. Flares and CMS occur more frequently, and the probability of Earth experiencing geomagnetic storms increases. Paradoxically, even though the Sun has more dark spots at this time, its overall brightness and visible light output actually increase slightly because the brightness of faculae around the spots outweighs the darkening from the spots themselves, raising the star's total luminosity by about 0.1%. The corona during solar maximum is filled with various streamers and loops, appearing exceptionally active with more frequent geomagnetic storms. Auroras are also more likely to appear at lower latitudes, allowing more people to witness this sky spectacle. So what drives this cycle? Scientists believe it's related to the charging process of the Sun's magnetic dynamo. Approximately every 11 years, at the cycle's peak, the Sun's magnetic field flips. Its north and south magnetic poles swap places, like a magnet suddenly reversing direction. More accurately, the solar cycle is essentially a 22-year magnetic cycle because it takes to 11-year cycles for the Sun's magnetic field to return to its original polarity. Within each cycle, sunspots first appear at mid-latitudes, then gradually migrate closer to the equator. This pattern is called Spira's law, often visualized in the famous butterfly diagram. This cycle isn't as precise as clockwork. Some cycles are slightly longer or shorter, and their intensities vary sometimes. The Sun also experiences anomalously quiet periods spanning multiple cycles, like the Maunder minimum in the late 17th century, where almost no sunspots were observed for about 70 years. This period coincided with Earth's little ice age. Solar activity might still be influencing Earth's climate in ways we don't yet fully understand. In contrast, the current 25th solar cycle is intensifying with a surprising number of sunspots, indicating Earth is in an active solar maximum. For a technology-dependent human society, the solar cycle is like a rough clock for space weather risk. During solar maximum, governments and satellite operators maintain high vigilance, ready to respond to potential solar storms during solar minimum. Though the Sun appears calmer, it doesn't necessarily mean it's safer. A side effect is that, as the solar wind weakens, its shielding effect against cosmic rays also decreases. More high-energy particles from distant supernovae penetrate the inner solar system, reaching near Earth. This poses risks to astronauts and high-altitude flights, because these energetic particles can damage human cells and affect equipment operation. However, beyond the Sun's internal cycles, external influences could also alter the solar system's fate. We must not forget that the solar system slowly drifting through the Milky Way, the gravity of passing stars could disrupt the delicate balance of planetary orbits. Recent research reveals that when influenced by broader galactic forces, the long-term stability of the solar system might be more fragile than we imagined. Our home is not as safe as it seems during the Sun's billions of years of existence. It hasn't been stationary. It orbits the galactic center, oscillating up and down through the galactic disk amid the birth and death of surrounding stars, like swinging on a cosmic swing. Sometimes other stars pass near the solar system. On a cosmic scale, near might mean a few light years, rarely even less than 1 light year. On Earth, we might not notice such a distant passage, but the outer regions of the solar system can feel that faint yet significant gravitational tug. But what if a star came closer? Astronomers and dynamicists have long studied the stability of planetary orbits, considering only the solar system itself. The gravitational interactions between planets maintain a delicate balance, remaining largely stable throughout the Sun's lifetime, although, even without external influence, over 1 billion years, there's a very small chance Mercury or Mars could be ejected due to internal chaos. That's not our main focus here, as we know. The solar system is not an isolated island. We live in a star-rich galaxy. Given enough time, the probability of a close stellar encounter increases. Recent studies aim to determine how such stellar flybys might affect the solar system's future, and the results are both astonishing and concerning. In a 2025 study, scientists simulated the evolution of the solar system over the next 5 billion years, including gravitational perturbations from passing stars based on current knowledge of galactic stellar density. They ran thousands of simulations of random stellar encounters. The results indicate that earlier models ignoring passing stars were likely overly optimistic about the solar system's long-term stability. Our home is more susceptible to external disturbance than imagined. Even a small star with a mass only 1/4 that of the Sun, if it passes within less than 100 astronomical units, could impart tiny nudges to the planets. These nudges accumulate or trigger chain reactions, ultimately leading to chaotic outcomes. In some cases, the effect of these perturbations is minimal, but some simulations show that a single close stellar encounter could completely alter the solar system's architecture, leaving planetary orbits unrecognizable. How drastic could the change be? Research suggests random passing stars could increase the probability of planetary instability several-fold. For example, Pluto, stable in isolated models, when stellar flybys are included, has about a 5% chance of being ejected from the solar system or colliding within the next 5 billion years. And Mercury, the most vulnerable due to internal chaos, sees its probability of instability under stellar perturbations increase by 80%. Specifically, this means the probability of Mercury eventually colliding with Venus or the Sun rises from a baseline of less than 1% to 1.8%, a small chance, but not negligible, like a time bomb hidden in the future. The surprises don't end there. Simulations show that over the next 5 billion years, the probability of Mars being ejected from the solar system or colliding with another planet is about 0.3%, and the probability of Earth, due to accumulated perturbations, being ejected into deep space or suffering a catastrophic collision is about 0.2%. On a 5 billion year timescale, this number seems small, but the probability is not zero. In fact, it's a sobering number. Before the Sun's life ends, the probability of Earth's orbit becoming unstable due to external stellar influence is about 1 in 500. More surprisingly, when such instability is triggered by a passing star, it often leads to the loss of multiple planets, and it happens earlier than in isolated simulations. In many cases, if a truly close stellar encounter occurs, chaos could unfold within the next 1 to 2 billion years. At such close range, the smooth functioning of the solar system we take for granted, those stable orbits we assume are constant, could completely disintegrate. Comets in the Oort cloud would almost certainly be disturbed, flying inward like a swarm of runaway meteors. Researchers note that over the next 5 billion years, the probability of a star passing within 100 astronomical units is about 5%. Should such an encounter occur, all possibilities for the solar system's long-term stability would vanish. Our home might meet its end in a gravitational storm from the outside, yet, even as we contemplate these distant possibilities, the Sun continues to surprise us in the present with advancing telescope and observatory technology. We are gradually uncovering the details of the Sun's behavior on the smallest scales, seeing aspects never before witnessed. A recent breakthrough discovery reveals that even the Sun's seemingly calm surface hides fine structures we never anticipated. Its mystery runs deeper than what we see. To understand the Sun more deeply, scientists built the world's largest solar telescope in Hawaii, the 13-foot aperture Daniel K. Inouye Solar Telescope. In 2025, during its first observational missions, the telescope achieved a stunning feat. It captured the sharpest ever images of the solar surface, revealing ultra-fine magnetic structures only 12 to 30 miles wide. For reference, 0.12 miles is about the length of Manhattan Island. On the scale of the Sun, about 1 million miles in diameter. This is undoubtedly minuscule, like seeing a single human hair on a basketball. These tiny magnetic striations undulate along the edges of solar granules, appearing as alternating bright and dark thin lines, extending along the boundaries of convective cells in the photosphere, like intricate embroidery on the Sun's surface. What are these striations? The research team explains. They are caused by sheet-like magnetic fibrils crossing granule boundaries when hot plasma rises within one granule and descends in adjacent downflow lanes. Magnetic fields form vertical magnetic fibrils. Light passing through these fibrils is modulated. If the magnetic field is slightly weaker, the light appears slightly darker. If slightly stronger, the light appears slightly brighter. Ultimately, at the granule boundaries, this creates alternating bright and dark stripes, revealing subtle variations in magnetic field strength over scales of just tens of miles. Essentially, this is the smallest scale magnetic fingerprint directly observed on the Sun, the most hidden form of the solar magnetic field. Although high-resolution magnetic simulations had hinted at these features, it's only now they've been directly observed, as if the Sun has finally revealed its microscopic face to humanity. These magnetic fibrils might influence the process of energy transport upward from the solar atmosphere into the corona, and the fact that the sun's magnetic field has such fine structure could be key to solving larger mysteries. Small-scale magnetic fluctuations might collectively contribute to chromospheric or coronal heating, or inadvertently trigger larger-scale eruptions. The Inuit telescope team emphasizes that understanding this fine-scale magnetic structure is crucial for more accurately predicting space weather. The more we understand the sun, the better we can protect ourselves. Yet, even as we decipher the sun's current behavior piece by piece, we also gaze continuously into its future. What fate awaits our star when its fuel is exhausted? The coming chapters are destined to be dramatic and likely quite brutal for the solar system's planets. It is an inescapable destiny. Today, the sun is in midlife, settled comfortably in its main sequence stage, stably fusing hydrogen in its core. But like all stars, its core will eventually run out of fuel. When that happens, the balance it maintains will be utterly broken. In about 5 billion years, when human civilization is long gone, a tale in cosmic dust, the hydrogen in the sun's core will be depleted, transformed into helium ash. Thereafter, a violent transformation will unfold inside this star. When hydrogen fusion stops, the core, losing its outward pressure, will begin to contract under gravity. This compression has an interesting effect. It actually makes the core hotter. Meanwhile, in a shell of hydrogen surrounding the core, previously too cool for fusion, the rising temperature will ignite hydrogen fusion. Thus, as the inert helium core contracts, a thin shell around it suddenly becomes a new energy source. Like a backup fuel, the sun ignites for itself. Fusion in this shell actually releases more energy than core fusion did. The extra energy causes the sun's outer layers to expand enormously. Our sun will transform into a red giant. Its outer layers will keep expanding, its color shifting towards a deep red, like a fireball nearing life's end, yet growing more violent. Over tens of billions of years, the sun's radius will increase by tens to hundreds of times at its peak expansion. The sun's radius might reach about 1 astronomical unit, the current distance between the sun and Earth. In this scenario, Mercury and Venus will undoubtedly be engulfed by the expanding star's outer layers, vaporized into nothingness in the inferno. Earth's fate lies shrouded in an invisible mist. Some say it might narrowly escape being swallowed, only to become trapped within the sun's expanded atmosphere, slowly roasted into barren rock. Others say friction with the star's outer gases will gradually slow Earth's orbit, pulling it like a leaf tugged by gravity, ultimately spiraling into the sun, vaporized into nothingness. In either case, the outcome will be catastrophic long before the sun actually engulfs Earth. Its increasing brightness will boil away Earth's oceans, turning seawater into steam lost to space. Intense radiation will strip away Earth's atmosphere, turning the blue planet into a lifeless rock. Earth will no longer be a home for life, but a deserted hellscape. During the red giant phase, the sun's helium core will keep contracting and heating until it reaches a critical point. When the temperature hits about 100 million degrees, helium fusion in the core will ignite, For a star like the Sun, this process happens violently in a helium flash. Helium suddenly fuses explosively into carbon, lasting only minutes until the core expands and cools. Reaching a new equilibrium is like a brief, violent heartbeat. In the Sun's late life thereafter, the star will stably burn helium in its core for about 100 million years, converting it into carbon and oxygen. During this process, the star's size will shrink somewhat, its color becoming slightly bluer, like a brief final flare of vitality before the end. When helium fuel is exhausted, the Sun's mass is insufficient to ignite carbon fusion. It lacks enough gravity to compress the core to the temperature required for carbon nuclei to fuse. The core will contract again, and the star will expand a second time. But this expansion will be more violent and more unstable. The Sun will become extraordinarily large and unstable. In its final stages, it will lose a significant amount of mass. Pulsations and intense stellar winds will blow its outer layers into space, bit by bit, like a planet shedding its skin. In its final struggle, our star will completely eject its outer shell, leaving only a hot, exposed core. This exposed, intensely hot core will flood the surrounding expanding gas with strong ultraviolet radiation, causing the gas to fluoresce. This forms a planetary nebula, a somewhat misleading name, as these glowing gas shells around dying stars have nothing to do with planets. Our Sun will release its magnificent nebulae into space like one or more shells of colorful gas, slowly expanding in the cosmos for tens of thousands of years. This nebula will keep expanding, illuminating the surrounding interstellar medium, becoming a transient yet beautiful sight in the universe, the Sun's final gift to the cosmos. Yet, knowing all this also contains a kind of ineffable beauty. We stand on Earth, bathed in the light of an evolving star, a star that connects us intimately to the universe's beginning and the solar system story's end. Every calcium atom in our bones was born in the core of some star. Every photon that turns leaves green was imprisoned in the Sun's furnace for hundreds of thousands of years. Before reaching Earth, we are fundamentally children of the Sun. It forged our bones from cosmic dust, nourished every green leaf on Earth with light it held captive for millennia. As long as it continues to shine, life on Earth has the chance within this star's radiance to continue writing more of life's untold mysterious stories. All right, my friend, let's pause our conversation here tonight on the mysteries of the universe. Now, allow me to press pause for you. Set aside all thoughts and inquiries and simply, quietly be in this moment. From here, my voice will fade away, leaving only the silent tapestry of the cosmos and a carefully chosen piece of pure music tuned to 432 Hz. Science suggests this frequency resonates deeply with the natural vibrations of the universe and the rhythm of life itself, soothing your nervous system and guiding you into deep relaxation. Now, find your most comfortable position. Gently close your eyes or let your gaze rest softly upon the stars. May you release all weariness from the world, letting your consciousness drift on the waves of music, floating into boundless tranquility. Good night, sweet dreams, until we meet again among the stars.